Dr. Louis Ziska is an associate professor in environmental health sciences at the Mailman School of Public Health at Columbia University. After graduating from the University of California, Davis, he began his career as a Smithsonian Fellow and then took up residence as the project leader for global climate change at the International Rice Research Institute in the Philippines before a 20-plus year career at the USDA's Agricultural Research Service. He's worked primarily on documenting the impact of climate change and rising CO2 levels on crop selection for CO2 responsiveness to improve production, climate and agronomic pests, including chemical management, climate, plant biology, and public health impacts from pollen to medicines. Dr. Ziska is a contributor to the 2014 IPCC report, Food Security Chapter, the 2014 and 2018 National Climate Assessment, Public Health Chapter, and Air Quality Chapters, respectively, and the impacts of climate change on human health in the United States, a scientific assessment. His most recent book is Agriculture, Climate Change, and Food Security in the 21st Century, Our Daily Bread, through Cambridge Scholars Publishing. Please join me in welcoming Dr. Ziska.
Well, thank you, Dr. Phillips-Bourne. I really appreciate the opportunity to talk about climate change and plant biology in the framework of public health. And if you hear singing in the background, my wife is a music teacher and she's teaching her students how to sing on a different, whole different class. But I understand from her that if you're a bass, Zoom is better, but if you're a soprano, it's better if you go to Skype. So who knew? I mean, different things that you learn as you teach. Anyway, I want to sort of begin by giving you this personal, professional, financial relationship with industry issue. I don't have any conflicts per se, but you may want to take a closer look at it depending on where you're coming from. Although I will say that my check from Al Gore is consistently late, so just so you know. Right, go on here. Before we talk about the health impacts, I want to sort of give you the scientific grounding in the context of climate change. We know that when you burn fossil fuels, the source of that fossil fuel is carbon rich. And so it can be anything from oil to coal to natural gas. But basically, when you oxidize something that's carbon rich, carbon dioxide is a product of that oxidation, of that burning. So we know that about 90% of humanity's carbon dioxide comes from the burning of fossil fuels and cement. About 10% comes from land use change, including, and maybe it's slightly higher number now, including some of the ag contributions. Where does all this additional carbon dioxide go? Well, about 50% of it stays in the atmosphere. About 25% of it is reabsorbed through photosynthesis in the land, and about 25% of it is dissolved into oceans, making the oceans more acidic. I'm sure you're probably familiar with many of these attributions. If you look at the recent change in carbon dioxide, this is the Keeling curve. It's the longest continuous record we have of carbon dioxide in the atmosphere. Beginning in the late 1950s, it's gone up from about 315 to about 400 and I think 414 last time I checked. An overall increase of about 30% in my lifetime. So if you go back in time, you'll find that there have been times when the CO2 has been consistently higher, but at least for the last million years or so, it's stayed between 200 and 300 parts per million. So this change that we're seeing is really unprecedented from a geological perspective. It's almost instantaneous. If you look at the future in terms of where the carbon dioxide concentrations are going to be by the end of the current century, there are a lot of different models. I won't go through all of them. Just to point out the two extremes, the green line here at the bottom is the everyone hold hands, drive a Prius, turn your thermostat down line, which is certainly possible, but probably not very likely. This dashed line is the business as usual line where we do nothing. And that's looking like it's probably not going to happen either. So we're going to be closer to the business as usual line but somewhere between these two lines in respect to overall carbon dioxide concentrations, probably anywhere from about 550 to 800 parts per million. So with all of that in mind, the big question then becomes, yeah, so what? Why should you care whether carbon dioxide is 400 or 500 or 600 parts per million? What difference does it make? There are two reasons. The first is one that you're probably familiar with, and that has to do with the indirect effect of rising carbon dioxide on warmer temperatures. If you look at the atmospheric components, you'll notice that nitrogen and oxygen are the primary components. But there are two special components, carbon dioxide and water vapor, that are referred to as global warming gases. What does that mean exactly when we talk about a global warming gas? What does that constitute? And the best way I can explain it to most of my students is that it has to do with music. So I'm sure some of you have played a stringed instrument at some point. And if I turned to you and said, hey, if I tune two strings of my instrument that are side by side to the same frequency, and I pluck one string, what will the string that's tuned to the same frequency that's right next to it do? And your answer will be, it will resonate. It will absorb some of that energy from the first string. Just a very basic principle of physics. Well, what works for guitars also works for global warming gases, except they don't absorb, obviously, in the key of A, but they absorb in the key of infrared. The molecular structure of the bond length is such that it will resonate under conditions of infrared radiation. And when it does so, it keeps some of that heat from otherwise leaving the Earth, the surface of the Earth, keeps the Earth a little bit warmer than it would be otherwise. And that's not a bad thing, because if there was no CO2, if there was no water vapor, the average surface temperature on the Earth would be minus 18 degrees Celsius. We'd be living in a very different world. So this is a natural greenhouse effect. We've known about it for 150 years. It's not controversial in the least. But you can sort of get a sense, however, of what we would refer to as the Goldilocks effect. That is, too much carbon dioxide or water vapor and things get too warm, not enough and things get too cold. So as we're adding more carbon dioxide to the air, we're going to see an increase in overall surface temperatures. Again, this is something we've known for 150 years. But the little twist I'll add on to this observation is that the temperature increase is not uniform. When we talk about global warming, we're talking more about areas warming faster, other areas not warming as fast. And the reason for that has to do with the nature of these two different molecules. So for example, if I go to the equator where it's warm and moist and humid, well, water vapor is going to be the dominant greenhouse gas. Yes, it will get a little bit warmer with more CO2. It will get a little bit wetter with more CO2. But the relative effect of rising CO2 is not going to be as great as where water vapor isn't present. So if you go to the equatorial regions, water vapor, humidity is going to be the primary driver for climate change. But if you go to places like the poles, where the air is dry because the air is cold and can't hold a lot of water vapor, the effect of CO2 is going to be much more dramatic. If you go to the deserts where the air is dry, the water vapor is low, the change in temperature is going to be much more dramatic. Similarly, if you go up in altitude, the area becomes drier as you go up in height. So it's going to be more of an effect. If you look at it from a seasonal perspective, winters versus summers, humidity in the summer is higher, so the overall effect in terms of rising temperatures in the summer is going to be less than it is during the winter. Hopefully, I've condensed a lot of the physics and geochemistry down to very simple explanation, but I hope you get the gist of this, and that is that if water vapor is high, it's the dominant warming gas, and there's little effect or relatively little effect of CO2. But if water vapor is low, adding CO2 is going to increase the surface temperature more. And that differential effect, some areas warming fast, some areas not warming fast, can do everything from change the jet stream to cause oceans to become produce more virulent storms. And so all of these are impacting in terms of the physical context of weather and climate. So from a plant biological perspective, You see that less temperature, water vapor is high, more precipitation, dry becomes drier, wet becomes wetter, etc. And of course, you have changes in sea level rise, all of which are going to affect the overall plant demography, where plants grow, what plants are going to grow there, and so forth. From a plant biology point of view, that's very interesting. Now, here's the second reason why you should care about the rise in carbon dioxide. Here's the reason that you won't see a lot of. Here's what often is considered to be controversial, or it is considered to be a silver lining in the rise of carbon dioxide. And that is, we know that plants are essential to life. You don't have plants, the rest of us are going to be in deep doo-doo. So what do plants need? Well, plants need light, they need water, they need nutrients, and they need carbon dioxide. About 90 to 95% of all plant species lack the optimal amounts of carbon dioxide to grow. So as carbon dioxide is taking off in the atmosphere, they're going to be affected. Now, that sounds good, right? So it's going to affect plant biology, and it must be affecting it in a good way, right? Well, maybe. So here's some pictures from loblolly pine. These were on the ExxonMobil website. And you can see it going from 385 parts per million CO2 to 835 parts per million CO2. Hey, loblolly pine grows more. That's great. That's wonderful. I'm very glad for loblolly. There's something, though, that wasn't mentioned on the ExxonMobil website. What could that have been? Well, it turns out that not all plants are beneficial. If you're at Emory University, I'm pretty sure you've seen this plant. This is kudzu, and you're all probably familiar with it. Hey, and guess what? Kudzu also responds to carbon dioxide. It turns out that CO2 is neither a Republican nor a Democratic molecule. Who knew? So when you look at the change in carbon dioxide, yes, you understand the effects in terms of climate, but it's also going to affect every single aspect of plant biology. And we don't talk about that because it's sort of segregated into it's all good or it's all bad. And so it doesn't make for good media coverage. So there are consequences of this, however, for plant biology, as with climate. CO2 is a fundamental resource. Not all plants are beneficial to human society. Not all plants are going to respond the same way. And if you affect how plants grow, you're also going to affect their chemistry. And that has some major, major repercussions. So let's look at what some of those are going to be and what I've been studying for the last 20 to 30 years. Well, it turns out, as you probably know, that climate can produce greater fire frequency. But what you probably don't know is that by changing the chemistry of the plants that are burning, you can also affect the intensity of the fires. So some of the grasses that are growing in the West we see as being impacted by the rise in carbon dioxide, so that their overall chemistry actually contributes to the presence of fire. What about narcotics? If you look at the role that public health plays in looking at opioids, one of the plants that is produced commercially is poppy. Well, it turns out that if you acetylate morphine, you can also get heroin. You look at cocaine, you look at any number of plant-based products that are contributing to the issue related to narcotics. And we don't have a very good idea of how climate and or carbon dioxide is going to affect the demography of these plant species or their chemistry or their ability to produce some of these narcotics. Again, our friend kudzu, it takes volatile organic carbon. It produces it. And when it produces it, that's a precursor for ozone production for places like Atlanta. So, and again, kudzu responds to CO2. As it responds to CO2, it produces more volatile organic carbons, which in turn have an effect in terms of ozone and so forth. Look about pesticide efficacy. If it turns out that your plants that you don't want to have around, i.e. weeds, are also responding to carbon dioxide, it makes it harder for them to be controlled through pesticides. What's the effect of that in turn going to be for pesticide exposure in public health? We're still working on that. What about food safety? Hey, it turns out that bacteria also respond to temperature, and that the possibility of you coming in terms of food poisoning as a result of E. coli or Clostridium or some other pathogen actually go up, because as things get warmer, bacteria grow more. Who knew? Changes, well, there's so many of these that are going on, but what I want to try and focus on for the remainder of my talk is to look at what I find is a really fascinating aspect of temperature and climate change in regard to human health. And that has to do with allergies, particularly the role of contact dermatitis and in the context of poison ivy, but also in terms of pollen and the sinusitis, the pollinosis, the asthma that is part of the exposure to pollen. And at the end, I want to sort of extrapolate that into the current COVID issue and seeing what you guys might think of that. So this is giant hogweed. This is a common weed in the mid-Atlantic states. Children often will snap it off, or they'll use the stems to play, swords, pirates, whatever. If that sap gets on your skin and the skin is exposed to light, then you will get what's called photodermatitis. And if it gets into your eyes, it can cause blindness. So this is one issue that has come to the fore. This is our old friend poison ivy. I'm sure you're familiar with it. Leaves of 3, let it be, roots like a rope, don't be a dope, et cetera, et cetera. And what we find is that, of course, it can also cause contact dermatitis. So let's take the second example here in terms of poison ivy and see whether or not it responds to carbon dioxide. And does it respond just by growing more, or does it change the chemistry of poison ivy? Well, let's see. Let's check it out. Well, let's check it out in a really sophisticated way. This is a free air CO2 enrichment or FACE site. This was done at the Duke University Forest. It was sponsored by the Department of Energy, which in federal terms we often refer to as the Department of Everything because they have so much money and we didn't. But basically what it does is each of these standpipes is blowing carbon dioxide into the center of the forest. And we're monitoring it, and some will open and push more in, some will close depending on where the wind is blowing. And the idea is to keep the CO2 elevated within the center of this ring. Okay, so this is our old friend loblolly pine, and not to make too big a deal of it, but it responds to carbon dioxide. But so does our old friend poison ivy. In fact, if you look at poison ivy in the context of how it responds, because remember, when you change your resource, not every plant's going to respond the same way. It turns out that, you guessed it, poison ivy responds much more than loblolly pine. So the mean plant dry biomass is exceptionally stimulated over a 6-year period. This is work by Jackie Moen, who's now at the University of Georgia, and she did an excellent job looking at it from how individual poison ivy plants are responding. Cool. We came in and said, well, wait a minute, maybe there's something else going on here. We know the poison ivy produces erythritol. That's an oil that causes the contact dermatitis. It basically acts as an epitope to your skin cells, turning your skin cells into a foreign body, and then having your immune system attack those cells in a way that destroys them. Often you'll get these blisters, clear liquid. Well, clear liquid is simply your lysed skin cells. So we wanted to see if you change the chemistry of poison ivy with exposure to carbon dioxide, and in fact it does, and I won't go through all the machinations of it. But basically, if one of the things that the NIH had shown in a previous publication was that the degree of virulence, the ability of a leaf to produce the contact dermatitis, was related to the unsaturated, saturated congeners within the erythritol. And we were able to show that with more CO2, in fact, you change the chemistry in such a way that it was going to produce a more reactive form of the erythritol, and contact dermatitis would go up. So not only is carbon dioxide causing more poison ivy, but it's also changing the oil of poison ivy in a way that makes it more virulent. So it's hard sometimes to get around this idea that, well, CO2 is plant food and it's all going to be great. It's a little more complex than that. And this, I know, there's actually a website that shows you all the different, if you want to share a picture of what your poison ivy rash looks like. I'm not, it is what it is. Here's another one, Parthenium. Hysterophorus is a noxious weed in America, Asia, Africa, and Australia. And hey, it's got the best of both worlds. Not only does it cause contact dermatitis, but it also produces pollen that is allergenic. So it's the best of everything. And this is an advertisement in South Africa saying that Parthenium is dangerous, it invades crops, it can cause poison for crops who eat it, it taints their milk and meat, so forth. It's a nasty, nasty plant. And here we are in USDA, and we're looking at carbon dioxide changes, not of what's going to happen at the end of the century, but what's already occurred. That is the carbon dioxide change from 300 to 400 parts per million. And the ones that are pre-industrial level here for the Parthenium, and here are the ones that are grown at the current level. And yes, there's a lot of plant-to-plant variation, but what we're seeing is that plants grown at the current level of carbon dioxide are already showing a strong increase relative to recent changes in carbon dioxide. This is the concentration of parthenon. We were interested in this because this particular plant produces a chemical that is an allergic defense compound. And we saw that it varied depending on both the biotype of the Parthenium, but also in context of more carbon dioxide. So, and there's differences between the biotypes. We had a Claremont showing a very strong increase. The other biotype, Tupulawa, not showing so much. So the more invasive variety in this case of Parthenium had much higher concentrations, especially when grown at current CO2 levels. So this is really interesting. Just to give you some broader view now, we're going to segue from looking at contact dermatitis to looking at pollen directly. And these are just different weeds that are associated with different regions of the country in terms of when they come out and how they contribute in terms of pollen load. So pretty straightforward. I won't go through all the machinations of it. You'll see ragweed showing up in all of the different regions. But basically, in terms of the pollen season, or at least the plant-based pollen season, you have trees primarily in the spring, oak and maple in the summer. You have weeds and grasses. The pollen loads drop precipitously, and then they kind of bump back up again in the fall with common ragweed and the variations of ragweed, giant ragweed, short ragweed, etc., that are part of the fall landscape. So of course, from our perspective, we wanted to see how common ragweed was going to respond to carbon dioxide. So we did this work late 1990s, looking at different carbon dioxide concentrations, and wanted to get a sense of how CO2 was going to affect ragweed. And again, we looked at pre-industrial 370, which was the CO2 at the time, and then 600 sometime that will a CO2 value that will occur sometime this century. This is the dry weight of the plant, obviously increasing with more carbon dioxide, but perhaps the take-home message is pollen production. This is on a per plant basis. Pre-industrial from 5 grams, the CO2 in the 90s to 11 grams, and then 20.5 grams. And what was interesting is that Ben Singer, who was a med student at the time, I think at Northwestern, wanted to do some antigen work on ambient A1, which is the primary protein on the surface of the pollen on the exene that causes the reaction. And here he's just showing that the ELISA test is also increasing with more carbon dioxide. So not only are you seeing bigger plants that are producing more pollen, but the allergenicity of that pollen may also be going up. Now, in fairness, we've never been able to repeat this, in part because I'm going to segue to some outdoor studies, and trying to capture pollen in sufficient amounts to do the ELISA test in an outdoor study is a royal pain, almost impossible. So we're going to segue to a different study. This was work done by Jaewon Oh in South Korea, 3 open-top chambers at the National Institute of Forest Science. And here he's growing the tree part. Now we looked at the ragweed part, now he's looking at oak. And oak under different conditions, CO2 conditions, to determine how carbon dioxide was going to affect oak pollen. And here's some of his data, total number of pollen grains and the mean diameter of the pollen grains. Again, he's looking at the CO2 treatments at ambient, which is the ×1, ambient CO2 1.4 times, and then 1.8 times. So the number of pollen grains per tree, and this is in billions, you get a sense of just how much pollen a single oak tree can put out. And then this is the pollen size, where there's also a significant change, although it's a little bit harder to see. Here he has some really interesting data, not just in terms of pollen weight per tree, which is obviously going up, but in this case on Quercus A1, which is the allergenic protein, again, on the pollen exene that causes your reaction. And here, as with ragweed, he was able to look at how carbon dioxide is also not only increasing pollen amounts, but also increasing the allergenicity of oak pollen as well. So I thought this was really cool. A little more sophisticated study. This was a study done by Julie Wolfe, who's postdocing in my lab at the time. You may have heard the expression hay fever. Well, it actually refers to Timothy grass, which is often used for hay. But Timothy grass is its own source of allergens through its pollen. And one of the things that is interesting is that when you bale Timothy grass, after it's been cut and baled, it will be infested by Alternaria. Alternaria alternata is a fairly common fungus, and it can produce spores. And so the spores it can produce can also cause respiratory issues, rhinitis, asthma, allergic dermatitis, etc. And so we wanted to see if there was potential interaction between carbon dioxide stimulation or chemistry of the Timothy grass and how that impacted the overall ability of Alternaria to produce spores. So to make a long story short, if you look at the different runs here along CO2 concentration, what you found was that the ability of Alternaria to produce spores was much greater in the high CO2 value. Why? Well, in part because the plant was bigger, but also in part because when you grow these plants under higher CO2, the nitrogen levels tend to fall, the protein levels fall. And it turns out that if you're a fungus and the protein levels are high, you're going to grow lots of hyphae and you're going to keep growing. But as the nitrogen level starts to diminish, as the protein levels start to go down, you're going to start to stop. You're going to stop producing hyphae, and you're going to go into reproduction and make more spores. So we thought this was a really elegant, really interesting bit of information in the context of CO2 and how it interacts with other organisms. Now, all this is great. This is fun. This is cool. This is interesting. Yeah, but it's a lab study. What does it have to do with the real world? So the problem with doing this kind of a work is, as you can imagine, it ain't cheap. I show you our old friend, the FACE system here at Duke University. These giant rings that are out there that, here we are again. Well, this was running, I think, just in CO2 alone, $1 million a year. They basically, this dark line that you see here is a railroad spur. They had to bring in a railroad car every day, 6 tons of carbon dioxide to fumigate this ring, in each ring, in order to increase the carbon dioxide within the center here. I didn't have $1 million a year to do this kind of work. So how am I going to, try and look at a real world study, manipulating a forest or manipulating anything in terms of carbon dioxide? Oh, and not just carbon dioxide, but temperature, because hey, both things are going to go up. So how do we do that? Well, I was reading a biography of Charles Keeling, and I kept thinking, why did he decide to monitor CO2 in Hawaii? Well, maybe he likes Hawaii. I don't know. I mean, they have great daiquiris and everything, timeshares, whatever. But there's a reason why. There's a method to the madness, and it has to do with geography. Hawaii is the most isolated spot on Earth geographically, and you're monitoring carbon dioxide at 10,000 feet for a reason, because you're not seeing human-derived carbon dioxide, let's say from, Honolulu. You're monitoring background carbon dioxide. Oh, so ground level carbon dioxide is not always going to be indicative of what is being measured on Mauna Loa. If that's the case, then maybe we can use that to our advantage. Can we look at ragweed in real time? Going from a rural environment, which because it's limited in terms of CO2 emissions from industry, should be closer to a control, if you will, to go to the suburbs and then go to the city. In this case, the city is Baltimore. So we dug our plots, we moved our soil. The soil had the same seed bank in it. I forget, 35, 40 different seeds. We made the soil uniform. We monitored the soil. I'm sorry, as an academic, I got to show you at least one slide with a lot of numbers on it. So this is just looking at daytime carbon dioxide. This is done in the early aughts. You can see as you go to the urban areas, CO2 is not stable. It goes up during the day. Nighttime temperatures higher in the urban areas. The change in season length, that is the number of frost-free days, is longer in the urban area. Daytime air temperatures are warmer. Yeah, what else is going on though? We were concerned about ozone, but whenever we saw an ozone peak happening in the urban area, basically within about a 6 to 7 hour period, it was also happening out in our countryside. So we thought this was not a perfect means by any stretch of the imagination, but it was a cheap means to try and simulate future environmental conditions. And you can say what you like to about necessity being the mother of invention, but I would argue to you that poverty is the father. Anyway, so we put out our plots, we tamped them down, we put out our in this case, rotor-rod pollen monitors, and we looked at ragweed. Now this time it's ragweed outside growing along this transect, and this is the rural site. These are day of year, where day 1 is January 1st, day 365 is December 31st. Now, ragweed is a short day plant, which in botanical terms means it has to, it'll only start to flower when the days get short after June 21st. So here it is, it's doing its little thing. All this is the pollen underneath it, in grains per cubic meter. And then we move to the suburbs, and these two arrows are essentially this starting point for the control and the maximum point. And you can see when you get to the suburbs, it's starting earlier and peaking, but downtown urban site, man, it is going to town. The area under the curve here is about 10-fold what it is here. So the average ragweed plant growing in urban areas is producing about 10-fold more pollen than here. Now, why is that? We're not entirely sure. Part of the sacrifice we had to make is we couldn't control individual variables using this kind of an approach. We know that the urban locale has a longer growing season, has a milder winter, warmer temperatures, more carbon dioxide. Those are all contributing to this, but we don't know which is contributing more than the other. And this is in the Journal of Allergy and Clinical Immunology. Cool. Okay, we've gone from the lab, we've gone to a rural urban transect, an outdoor study. Gives it a little more validity, maybe. I don't know. But yeah, darn, it's a global problem. We've got to approach it from a global perspective. How do we do that? How do we do that? Okay, well, now, boy, yeah, now the money is, there's no way. Well, maybe. Remember what I was saying about CO2 and water vapor? Remember what I was saying that in places where it's warm and humid, you're not going to see as much of a change as places where you're more colder? So maybe the latitudinal gradient will work, and maybe it might work in real time, because if there is this relationship between CO2 and water vapor, then the colder climate should be warming much faster than what's happening down on the Gulf Coast. So we used that, and I called a lot of allergists and medical doctors on the phone and said, "Hi, you don't know me, I'm from USDA, don't hang up, don't hang up." Some of them didn't hang up, and they were interested in what I had to say, and they were very, very cooperative in being able to provide data. Now, in this instance, it was kind of a mess in terms of how pollen was being monitored. Some were using rotor-rods, some were using Burkharts, all different kinds of ways. So the absolute numbers were difficult to look at in terms of pollen mode. But what we could look at was the season length, and whether or not there was a change in season length with latitude. And so we looked from June 21st to the first frost. We had the different kinds of measurements here, and I won't go through all the specific details. They each have their strengths and their weaknesses. We did the rotor-rod sample. for our own work, and this is from PNAS. And what we saw, not a perfect correlation, but as we looked at the beginning and end of the ragweed season from 95 to 2013, we pretty much saw the trend that we expected. Now, it gets complicated because urbanization tends to come in some places like Minneapolis and St. Paul or Omaha probably contributed to the greater number of days. But the overall trend is pretty straightforward. And so what we're seeing in real time is a change in the season length of ragweed as a function of how different regions are warming differently in response to climate change. Okay, cool. So this is the different sites along here. This is the change in days to first frost. This is the change in frost-free days. Clearly, the northern latitudes are warming up faster than the southern latitudes. And if you want to get really fancy and look at latitude, frost-free days, and this is the change in the pollen season, you can see it along here. So, whew. Okay, we've gone from the lab and we've gone to a local, regional, urban, rural transect, and now we're on the continent. All right, we can stop there, right? Okay. Global monitoring. Oh, goodness. Yeah, the different colors here, most all the monitoring has been happening in the northern hemisphere, obviously. And the different colors refer to the different methodologies. It's almost all Burkhardt. In Europe, it's a mixture of Burkhardt and Rotorod, some automated ones. Not much is happening in the southern hemisphere, and so we had to choose. Can we do it at a larger basis? Can we do it on a global basis in terms of trying to understand not just what's happening in North America in terms of temperature changes, but what's happening for the world? Let's see if we can do that. What the heck? So we went on a hunt, and we did a lot of emailing this time, not using the phone. And we talked to various allergists, various folks, and said, hey, you got any data for us? And they said, yeah. The oldest one we could find was Turku, Finland, where they've been monitoring seasonal pollen since the 1970s. And this is their seasonal pollen data from Turku. Here's some from Reykjavik. Not as long a set, but still pretty interesting. Let's see, here's one from Geneva. Again, you get a sense that certainly pollen counts are going up all over the world. And what we did is to then look at 17 different locations. There had to be some parameters. The first parameter was they had to use the same methodology for counting pollen all the way through whatever, at least a 20-year period. And then we had to be able to find the meteorological data, particularly for temperature, for that site or close to that site. And basically what this is showing then is, this is from a recent article in Lancet Planetary Health. This is the change in pollen load per year, the amount of total pollen per season, as a function of the cumulative temperature increase, the slope of the temperature increase over that 20-year period. So it ain't perfect, but there is, in fact, a significant correlation in real time on a global basis. So we think we might have found something here. Yeah, but there are always issues. Consistent metrics, again, talked about that. Automation, we're trying to get new sensors now to automate, to do the best we can to try and using the information technology and the software to identify and quantify pollen loads. It's a major task, but Pollen Sense, I think, is a company that is making some strides in that area. But I want to leave you with this. We know that pollen is related to allergy and asthma. And when you look at the allergy forecast, particularly for the mid-Atlantic, late April, what time is it? Oh yeah, today's late April, isn't it? So what's going on with the pollen in the sense that we know it's going to affect respiration? Is there a link there to respiratory viruses? Interesting. Here's a paper from Stephanie Giles. Pollen exposure weakens innate defense against respiratory viruses. The ability of pollen to suppress innate antiviral immunity, independent of allergies, suggests that high-risk population groups should avoid extensive outdoor activities when pollen and respiratory virus seasons coincide, which they're now doing. Is there a link? Could temporal and spatial intensity of seasonal allergies influence respiratory virus metrics? I don't know. But it's reasonable, I think, to suspect that there might be a link. And maybe post-COVID, we can begin to look at the nature of that link. Maybe we begin to look at children that we know typically don't respond to COVID, but maybe if they have high sensitivity to pollen, they do. I don't know. All I know is that there's a likely interaction there, and or at least potential interaction. And I'd like to begin to quantify that, to look at that. So we think there are links here between climate and pollen and respiratory viruses and other aspects that were directly related to public health. And in all fairness, we think that some of these links ought to be investigated. They should be looked at in a little finer lens, I think. So all that aside, I thank you for your attention. I hope it was at least reasonably interesting, and I'd be happy to take any questions.
Thank you so much, Dr. Ziska. That was riveting. I was waiting for your answer on pollen and respiratory viruses, so thanks for that cliffhanger. I'm looking forward to seeing what research does come out of this as it relates to pollen and respiratory viruses. We will, I guess, find out. Emily, who's been gathering our questions, I'll turn it over to her to ask them to you. And before you guys leave, join me in giving Dr. Ziska a round of applause and start our poll. A couple questions for course evaluation, if you don't mind filling those out as well while Emily is going through with our questions. Thank you so much again.
You're welcome.
So as of right now, if anybody has any questions, feel free to pose them to everybody or privately, because we don't have any questions at the moment. But I think one of the comments that I have in response to the final thing you posed is kind of the overlap of pollution in urban settings as well as the higher pollen burden. So I think specifically for COVID-19, it'll be interesting how they suss out those two as far as confounding is concerned. I don't know if you have thoughts about that, but I was just a thought I had.
No, I absolutely agree with you. I think from what little I've read, I've seen at least one study suggesting a very strong link between air pollution and COVID. And it would be interesting to see if there is how pollen pollution and respiratory viruses might interact along those lines. I think there's a lot here we just don't really comprehend yet.
Yeah, I think physiologically, like how do all of those sort of mediate maybe disease progression would be really fascinating right now.
Agreed.
And then one other question that I had for you, just because you have a great deal of experience, it sounds like working with governmental organizations, how do you use this research that you've been collecting that seems like pretty apparent to all of us, indicates that higher levels of CO2 definitely have an impression on public health negative consequences? How do you use that as a tool to affect change, or how have you found that to be successful in your career?
One of the things that I try and do whenever I give a presentation, particularly for lay folk, many people have heard the context of climate change in regards to the environment, and often they see that as a polar bear floating on an ice floe. And I have nothing against polar bears, but I think you can make a better impression if you can take climate change and plant biology and relate it directly back to the person's health, or to something that they understand, that they recognize. So some of the work that I mentioned briefly at the beginning, when you're looking at changes in food safety, many people have had food poisoning. And if they see a link between climate change and pathogen availability and what that means for food poisoning, they're going to pay attention to it. or what effect it might have on nutrition, or what effect it might have on pollen, or what effect might it have on plant-based medicines. All of those, I think, are things that people, for the most part, can relate to. It affects them directly. And I think that's one way to sort of get them on board in terms of understanding what the impact of climate change will mean in their daily lives.
I think, yeah, I think that seems really true. Making it very relatable would be super helpful. There is a question from Ben at Emory. What role can sustainable agriculture practices play in sequestering carbon?
They're not a panacea. They're not a one-size-fits-all kind of role, but what they can do is twofold. One is the sustainable practices, which can include everything from no-till to cover crops to greater crop rotations, can play a role in um, making sure that food is available, but also may play a role in terms of improving soil health so that soils can take up additional amounts of carbon dioxide. It can also play a role in, depending on the crop, on other greenhouse gas emissions. So for example, in rice, which is typically flooded, methane is, because of the reduced conditions in the soil, methane is usually a byproduct. It comes up from the soil through the rice and into the atmosphere. But if what's happening now with climate is that as freshwater sources become scarcer, as they become harder to get, then the culture, the management of rice is changing. And we're looking for ways that can still maintain rice yields, but use less water. And so when we go to farmers, we can say, look, I don't, whether or not you care about greenhouse gases, but hey, you can save some bucks if you use less water. Here, we've got the data to show you how to do that. Oh, and by the way, you're going to reduce methane. So it's a win-win. There are some folks that are altruistic that will want to do this, but for the most part, using sustainable ag and the economic incentives that sustainable ag has to offer, I think is a good way to move that forward.
I agree. A couple more questions that just came rolling in from Emily in M3 at Jefferson. Have you studied any methods of urban planning that have been successful in not only decreasing carbon emissions, but mitigating the oversized effects in cities?
Not on urban planning per se. What I have seen a little bit of is looking at what I call urban gardening, where you can do a number of things. One of the obvious ones is increasing green space. When you look at how temperature is distributed in an urban area like New York City, for example, you'll find that there's almost a social economic predictor of what temperature is going to be during a heat wave. So the South Bronx is going to be the hottest place in the city. Manhattan might be the coolest place in the city. So by greening, you can put, additional shade, additional means to cool down an area that typically will have higher heat extremes. But I would go a step further and I would add what I call edible greening, where not only are you going to plant a tree to produce shade, how about putting in a fruit tree where you can also provide shade, but also increase civic pride if you have a row of cherry trees down your avenue, or have fruit that's available to the local bodega, which normally doesn't get a lot of fresh fruits and vegetables, as a means to begin to counter the food deserts that we've been hearing about. There are a lot of opportunities there, but in the larger scheme for urban planning, I can't really offer much on that.
Yeah, I've heard a lot of those instances in cities where they've combined an effort to sort of mitigate food insecurity at the same time as providing different green spaces for carbon sequestration. And I think that's a neat intersection for sure. And then a question from Steph at Emory. I've heard in the past that allergies are more prevalent in the US compared to other countries. Is that true? And if so, what factors go into making allergies worse in the United States?
That's a pretty complicated question. I'm not sure I'm going to be address it all holistically. I can say that there has been work that has been done by Amir Sapkota at the University of Maryland and other folks that have looked at the role that climate change is playing in terms of increasing the allergy season, but also increasing the intensity of the season with more pollen occurring in the spring. And those are beginning to be recognized now as factors for why it might be more prominent within the US as opposed to other places. As far as comparing Europe and the United States, I'd say it's in flux. My understanding is, for example, that in Europe, particularly Eastern Europe, ragweed has basically become dominant, and that the allergies that are the people that have ragweed allergies is far greater actually than it is in the United States. As far as tree allergies, I don't have a good answer for that per se. So I think it's both temporal and spatial, and trying to compare the European allergy response to the US allergy response.
Interesting research to come, I'm sure, too, hopefully. And then David from the Icahn School of Medicine at Mount Sinai, do you know of any regions within the United States or other countries that have found great ways of incorporating plants into urban settings to mitigate? Oh, okay, we kind of answered that question. Let's see. And then last one, anonymous question. You talked about chemical and poison ivy becoming stronger, even as the plants grow faster and increase CO2 environments. Are there examples of other stronger respiratory allergens? That's a great question.
It's a good question. There may be, but we're unaware of them at this time. What we have seen, however, is that when you start looking at secondary compounds that are of pharmacological interest, that you can get both good and bad responses to those compounds. So for example, for one of the prominent anti-malarial compounds is referred to as artemisinin. It makes up artemisinin combination therapies, or ACTs. And working with Chinese colleagues, we were able to show that recent changes in carbon dioxide may actually contribute to a higher concentration of artemisinin. So that would be of benefit in terms of harvesting those plants for artemisinin compounds. Conversely, if you look at it, from an opioid point of view, then those concentrations can also go up with more carbon dioxide. So it depends on the species. It depends on the chemical of interest. And it depends on the response overall. We think there's a firm possibility of a definite maybe that if the compound has a lot of nitrogen in it, so some of the vitamins in rice, for example, that have a high nitrogen content, they would be adversely affected. So vitamin B9, I think, has a high nitrogen profile, and it will go down with more CO2. Conversely, something like tocopherol, vitamin E, will go up, in part because it has no nitrogen. So what we're seeing is basically the plants are reflecting to some extent what's happening in the atmosphere. They're becoming carbon rich but nutrient poor. And if you have a secondary chemical compound of pharmacological interest, then depending on the chemistry of that compound may either go up or go down. That's our working hypothesis at the moment.
I think that'll be interesting too, just on as far as like nutritional composition is concerned, like how that might inform our different recommendations as well for different vitamins.
Yeah, I didn't get a chance to talk about nutrition, but I think the role that temperature and nutrition will play is really fascinating.
Yeah.
Any more questions, Emily, or did we get to cover them all?
We got them all, yeah.
Excellent. Well, thank you again, Dr. Ziska. That was really wonderful. We are so lucky to have you. And for all of you guys on the line, after this lecture, I'm going to send out information for our 2 calls tomorrow, Jeremy Hoffman and Samantha Adut, talking about heat and child health, respectively. So thank you so much again, Dr. Ziska. I see the claps coming up, and we really appreciate you spending this time with us.
All right.
Okay.
Well, thank you all so much for having me. I appreciate it very much.
Thank you. Bye, everyone.